One of the interesting and cool things about surfaces, as we've already seen, is that you can find a tangent plane to a surface at a point. So if we say let S be a parametric surface given by the vector valued function r of uv equals x of uv times I plus y of uv times j plus z of uv times k over some open region D in the UV plane. See, that's our like interval. It's not like a T interval now. It's a region in the UV plane. You get translated as XY plane if you want to think of it like that. Anyway, such that x, y, and z all have continuous partial derivatives on D, our domain in the UV plane. Then the partial derivatives of the vector valued function R with respect to u and v are the following. The partial of r with respect to u and v is the partial of x, that's this one, with respect to u times I, plus the partial of this one with respect to u times j, plus the partial of this one with respect to u times k. So see why it's that? And the partial derivative with respect to v of our vector valued function is the partial of this one with respect to v, plus the partial of this one with respect to v. Sorry, I forgot to say times I. Partial of this one with respect to v times I, plus the partial of this one with respect to v times j, plus the partial of this one with respect to v times k. So, I wouldn't tell you about partial derivatives unless I also talk to you about what do they actually mean, and that's dicey, but we'll hopefully understand that. Okay, geometric meaning of these partial derivatives is the following. If v equals v0 is held constant, so that's this v, and if that's held constant, then r of u v0 is a vector valued function of a single parameter, hence a wire, and defines a curve C lying on the surface S. In fact, it's the intersection of the surface with the plane v equals v0, right? Think about that. We got a surface and it intersects the plane v equals v0 somewhere, and it makes a wire, if you will. The tangent vector at any given point, on any given point of that curve, say x at u0 v0, y at u z0, and z is u0 v0. In other words, I could tell you the point by giving you specific values of u0 and v0. Anyway, the tangent vector to the curve at that point would be r of u at u0 v0, which is xu of u0 v0 times I, plus y sub u of u0 v0 times j, plus z sub u of u0 times z0 times k. Okay, remember, that's in the plane where y equals v0. Or maybe I should say where v equals v0. Better said, sorry. That's a typo. So wow, is that a lot? In similar fashion, if we hold u equal u0 to be a constant, then r of u0 v is a vector valued function of a single parameter, see, because u0 is a number now, right? And so it's a wire and defines a curve E that lies on the surface S and is the intersection of that surface S with the plane x equals u0. As a matter of fact, this was, I did mean to say that, and I didn't say it rightly, so that was y equals v0. And the tangent vector to E at that point, right, is given by RV, R sub v if you want. That's like the subscript definition for partial derivatives. So the partial of r with respect to v at u0 v0, which is partial of x with respect to v of u0 v0 times y, partial of y with respect to v of u0 v0 times j, plus partial of z with respect to v times u0 v0 k. Wowie. So if the normal vector RU cross RV is not 0 for any UV in the domain, in other words, anywhere in the domain set D, then the surface S is called smooth. And why is that important? Because if it's smooth, it'll have no breaks and cusps, and it'll have tangent planes at every point in, well, tangent planes on the surface for all the points in the domain that surface is a vector valued function of. So smooth surfaces have no breaks, no cusps, that means sharp points, and this is the type we most often see, like spheres, ellipsoids, paraboloids. They're all smooth. A cone would not be at one point, and that's at the center point of that. It has a cusp, and you couldn't think of a tangent plane at the cusp, at the point, so to speak, of a cone. But to find such a tangent plane to a smooth surface at a point, it will involve finding a normal vector to the plane at that point, as the following indicates. So, how do you find a normal vector to a smooth parametric surface? Let S be that smooth parametric surface defined by the vector valued function R of uv equals x of uvi plus y of uvj plus z of uvk. So there's our vector valued function defining our parametric surface S. And that's defined over an open region D in the UV plane. A normal vector to the surface S at the point x of u0, v0, y of u0, v0, z of u0, v0 is given by the cross product, I'm calling it n, but it's a vector, ru of u0, v0 crossed with rv of u0, v0. That would take some manipulative skill to remember how do you find this cross product, and of course I've got a memory device. And so remember vector cross product ijk, one vector here, next vector there, that's how we do it. So here's how you do it. The vector r sub u of u0 v0 is the partial of x with respect to u here, the partial of y with respect to u there, the partial of z with respect to u there. So that would be that vector. These all have i's, j's, and k's attached, right? And then this vector is partial of u, partial with respect to v of x0, partial with respect to y of sorry, I'm not saying this right. Partial with respect to v of x, partial with respect to y of, I'm not saying the partial with respect to, start again. Partial of x with respect to v, partial of y with respect to v, partial of z with respect to v. Remember, we showed you that, right? Showed you how to find all those things. And so that is the normal vector. Now once we get the normal vector and a point, then we can easily determine the tangent plane. So here's an example of one of those. Now I'll do the example in the next video.